All right, welcome to this explainer. Today, we are diving right into the ultimate rulebook for surviving extreme industrial corrosion. We're talking about ASTM A789, a specification that dictates how some of the toughest, most resilient metal tubing on the planet is actually made. Think about this for a second. How exactly do you transport highly corrosive chemicals or deal with nasty, aggressive seawater without completely destroying your expensive equipment? I mean, in massive industrial setups, things like chloride stress and pitting will literally obliterate standard carbon steel. Even regular stainless steel doesn't stand a chance. Engineers can't just cross their fingers and hope for the best here. They need a highly specialized, mathematically proven solution. So here's the roadmap for today. We'll start by defining exactly what ASTM A789 is. Look at where it's used out in the wild, check out the standard specs, look into the testing and heat treatment, and then wrap up with the classic showdown, A789 versus A790. Section 1, defining ASTM A789. What is it? Let's establish exactly what we're looking at here. Okay, let's dive in. This official document, ASTM A789, and its metric twin, A789M, outlines the absolutely rigorous requirements for seamless and welded ferritic and austenitic stainless steel tubing. Basically, it's the holy grail rulebook for manufacturers. It guarantees the tubing they produce is going to survive general service in some of the most unforgiving environments on Earth without failing. To put it simply, it's a dúplex stainless steel tubing standard. Sure, it's engineered for general corrosion resistance, but the real star of the show? That's its intense focus on resisting chloride stress corrosion cracking. Look, if your facility deals with chlorides that cause stress-related cracking, which, let's face it, is an absolute nightmare for maintenance and safety, this is exactly the standard you need to be turning to. Now, what's truly fascinating is why we call it dúplex in the first place. It acts like a hybrid, kind of like a metallic best of both worlds. It's roughly 50% ferrite and 50% austenite. By perfectly balancing these two phases, the tube inherits incredible high strength and resistance to stress cracking from the ferrite, while getting the general corrosion resistance and workability from the austenite side. It's a brilliantly engineered combo. And this right here really brings those abstract specs into reality. These are perfectly engineered dúplex tubes undergoing strict quality checks right on the factory floor. They can be made seamlessly or welded together. But here's a fun fact. The standard strictly dictates that absolutely no filler metal can be added during the welding process. It has to be pure. Moving on to Section 2. Where is it used? Let's look at the real-world industrial applications of this stuff. You'll find A789 tubing acting as the critical veins for heavy industry all over the globe. Because it laughs in the face of aggressive environments, it's the absolute go-to material for heat exchangers and massive condensers. You'll also see it heavily utilized in chemical and pharma equipment, gas processing, and the pulp and paper industry. Basically, anywhere you have brackish water, intense bleaching operations, or specialty chemicals, these tubes are the unsung heroes keeping everything running safely. All right, Section 3, the standard specifications. What are the actual rules and requirements? Let's look at the chemistry. This standard strictly controls the metal's recipe. Take a super dúplex grade like UNS S31803, you might know it as 2507. The chemical makeup requires highly precise levels of chromium, sitting between 24 and 26%, molybdenum at 3 to 5%, and extremely specific doses of nitrogen. They don't just throw these elements into the melting pot and hope for the best. They are exactingly balanced to aggressively block pitting and crevice corrosion right at the microscopic level. And mechanically, the tubing has to be incredibly tough. Look at grade S32205, for example. It must hit a staggering minimum yield strength of 70 ksi, that's 485 megapascals, and a tensile strength of 95 ksi. To put that into perspective, these are exceptionally high-strength materials purpose-built to take on immense structural and internal pressures without warping or deforming. But wait, there's a catch. The standard issues are really crucial warning here. As tough as this dúplex tubing is, it is highly susceptible to embrittlement if you use it for prolonged periods at elevated temperatures. You literally cannot just install this in a high-heat environment, walk away, and forget about it. If it gets too hot for too long, that perfectly balanced 50-50 hybrid microstructure degrades, and the metal becomes dangerously brittle. Temperature control is everything. Section 4. Testing and heat treatment. Because getting the chemistry right is really only half the battle. The manufacturing process is actually heavily regulated. To guarantee that 50/50 duplex microstructure forms perfectly, the standard mandates a very strict heat treatment process. After the tubing is hot formed, it gets heated in a continuous or batch-type furnace. But here's the real kicker, the final step. The tubes have to undergo individual water quenching or some other method of rapid cooling. This sudden massive drop in temperature permanently locks in that vital duplex microstructure and all its protective properties. And they don't just box them up and ship them after that. They go through a brutal battery of mandatory tests. We're talking hardness checks, intergranular corrosion testing, positive material identification, the whole shebang. But what's absolutely make or break for this tubing are the flaring and flanging tests. Since these are mostly used in heat exchangers, they have to be physically flared and flanged to fit securely into tube sheets. If the metal cracks even a little bit during these tests, boom, it completely fails the standard. Finally, Section 5. ASTM A79 versus A790. Let's clear up a major point of confusion in the industry. People mix these two up all the time, but they serve completely different purposes. The big takeaway here comes down to dimensional standards. A789, the one we've been deep diving into, is strictly for tubing. It generally features smaller diameters and is measured by exact outer diameter and actual wall thickness. It's precision engineered for delicate things like heat exchangers. A790, on the other hand, is for pipe. Think larger diameters used for heavy structural fluid transport, and it's measured using nominal pipe size and schedule. Because A789 is used in super highly efficient, delicate heat transfer setups, it demands much stricter manufacturing tolerances. Notice how A789 holds a tight wall thickness tolerance of plus or minus 10%. A790 pipe allows for a much looser negative 12.5%. And remember those flaring and flanging tests we just talked about? Absolutely mandatory for A789 to guarantee perfect connections. For A790 piping, not mandatory at all. Understanding these nuanced standards is really the key to efficient, safe industrial design. You definitely don't want to use pipe when you need precision tubing, and you absolutely don't want to use standard steel where chloride stress is just waiting to cause a catastrophic failure. So, with its incredibly strict mechanical tolerances and that fascinating 50/50 duplex hybrid structure, it leaves us with one final thought. How could the ASTM A789 duplex powerhouse transform the safety and efficiency of your next high-stress project? Thanks for joining me for this explainer, and keep learning out there.